welcome to NPTEL course on power system protection. We are with the modules on network protection with renewable sources. In today's lecture, we will go into the concepts related to presence of renewable plants and the issues with transmission network protection, where we will see three issues: fault type classification, directional link, distance protections. Of course, there are other related issues in this domain also. Now, in this module, we have already addressed on the role of renewables and associated protections. In the last lecture, we talk about how the renewable sources affect distribution system relay performance and other allied protection issues. Now, to the transmission system, we say these days you can say that the renewables are being integrated at the transmission level also, starting from hundreds of megawatts to of the order of gigawatts also. So, this large scale integration to the transmission system, does it affect the transmission line protection? That is the question of this lecture. We like to consider that address on that perspective. What happens in this case? These large scale converter inverter renewable plants that consist of several such units, and the area coverage becomes pretty large. So, that introduces variability, how many units operating at a time, if it is solar, what is the amount of solar irradiance available at a time, variation among the units at a time, wind velocity across different units in the same plant. So, that introduces variability in the overall output of the plant. Fall right through compliance through different grid codes, that we have already discussed in earlier lectures also. So, that during fault voltage dips, but at high voltage system these units are not allowed to be withdrawn, otherwise further degradation in system stability will be challenging because of the large capacity. Different control schemes adopted in the inverter management system modulate the corresponding voltage and current during fault in particular significantly, that we have learned in fault characterization of the inverters also. Control grid code. Another point, system non-homogeneity, that which we already talked in distance link perspective, the impedance angle, that is a challenge, that is there is a difference in that perspective, and that is why I can say that network protection is under scrutiny. Let us come to a large scale renewable plant, where we have several such units depending upon the each capacity of the corresponding PV plant, its associated inverter, and then aggregation of that leads to a transformer, step up transformer, and such units are, you can say that in multiple units connected to a common bus, collector bus, and then again you can say that that large scale you can say that integration is being connected to a high voltage bus through another main transformer, a step up transformer. A typical example will be having 0.48 kV to 33 kV at first level and from 33 kV to 220 kV or 400 kV at the next level. So, these large scale renewable plants in the of the order of gigawatt or so can be connected to high voltage transmission system and then to the grid. Now, such a plant the arrangement leads to, you can say that the corresponding transformer connection is of importance on the operational and protection perspective, and so also the control and all control, and you can say that the grid code associated on the inverter, you can say that is also of importance in the perspective of protection. So, we have already addressed variability of output powers. We will see also, you can say that the corresponding source impedance variation, all these perspective you can say that makes the protection more challenging. Now, let us go into further details. Equivalent model of the renewable plant. We already know PV plant is being modeled as a current source. Now, in this case the corresponding synchronous generator is a constant voltage source with a fixed impedance and so series impedance, whereas a renewable plant is modeled as a control current source as shown here. Now, if you like to, we can say that consider as a voltage source, you can say that control source. For that perspective, representing either a variable voltage source with a fixed impedance or a fixed voltage source with variable series impedance. So, these are the two possibilities which you can consider the corresponding current source converted to a voltage source operating at a particular instant, because every instant the corresponding current source changes, and that is, you can say that we call as control current source perspective. The current angle is regulated by the converter's control, and that control action has to be satisfied with numerous grid codes, you can say that associated. Now, let us come to this German grid code perspective here, where the current you can say that versus the voltage perspective. So, you see you can say that V n I n the corresponding normal voltage and current, delta I q the reactive power injected, and the delta V are the changes in the reactive current and voltage during faults. So, this is a dead band gen, nothing like as they wish, but once you can say that the corresponding voltage changes becomes more and more because of the fault or so, then the reactive power contribution by the inverter becomes more and more for maintaining the system voltage and so. So, that is what we say the operational perspective of the inverter interfaced source as compared to the synchronous machine based source. Further, another North American you can say that grid code says renewable plants to ride through faults with unity power factor. So, these are the variations on the operational perspective of the corresponding converter during fault, how the current injection happens to be there, is it unity power factor, is it reactive power support, and so that makes the consider the corresponding fault current with respect to the voltage at that bus to be a different one as compared to the synchronous machine perspective. Variability in equivalent source impedance for such controllable current source introduces system impedance non-homogeneity, the angle of synchronous machine impedance and the angle of the transmission system impedance in our earlier distance link perspective was considered to be of similar value, but here that does not hold good because of these control operations and the corresponding equivalent impedance of the source that becomes that varies significantly with time even during fault, and also the corresponding associated angle. and that angle may not be similar value matching with the corresponding transmission system impedance. Now, on the sequence networks of renewable plant. So, the corresponding Poetti sequence network is this one, that is what the balance current it supplies. Now, note that we have already learned that such sources even during unbalanced fault also they provide balanced current, that implies no negative sequence current, no zero sequence current. Therefore, what happens that the negative sequence circuit is considered to be open, no negative sequence current from the source, no zero sequence current. So, therefore, these you can say that negative sequence network and zero sequence network happens to be open circuit. And most of the you can say that inverters, as already mentioned, are underground ungrounded, and that is why I can say that the corresponding zero sequence current becomes not available, even the fault happens to be involved with ground or so. And Poetti sequence current output gets modulated according to the applied control scheme. So, the corresponding output Poetti sequence current output also get modulated, and that you can say that changes the corresponding network impedance perspective accordingly. But we have already mentioned earlier also, presently in inverters the fault characterization says that less than 2 cycles the following the fault inception, the current can have a normal flow, natural flow, and during that period you can say that only some negative sequence current may be available. But that does not ensure that afterwards the negative sequence current will be available. So, negative sequence components based approaches on protection for network, which is being pretty common as you have learned earlier, may be under scrutiny, are under scrutiny. Some of the available standards in renewable plant interface inverters we configure asks for you can say that providing negative sequence current intentionally, so that available protection schemes and control schemes in the grid will be still functioning properly. Such a characteristic of renewable plant affects different sequence component based protection schemes, and that is the you can say that the question that how will be the performance of the network protection schemes. One important factor is on the transformer connections. So, we see two stages of stepping up the voltage at the first stage and the second stage. So, we see that the corresponding transformer connections. So, dy 11 and then you can say that this is dy 11 and this is yd 11. It means that the corresponding you can say that the angle at this stage and between this stage the corresponding network can say that the angle get cancels out with these two transformers, and that you can say that is being maintained in terms of that. Such transformer arrangements make the zero sequence current to be available at common coupling point. See or what happens to the zero sequence network in this case. So, earlier you have seen the sequence component of networks for positive, negative and 0 for the converter up to the converter. Now, with the for the transformer part. In the transformer part, the first stage you can say that for this dy 11 part. So, that becomes this, because we say this from the converter side, this side you can say that remains open, and this transformer you can say that is a delta y delta you can say that. So, therefore, you can say that for this one the circulating current will be finding to this reference. Now, this part is for the first stage, but the main transformer if you see you can say that delta side to this bus side, collector bus side. So, therefore, you can say that the circulating current to this one. So, that you can say that this will be to this one, and this will be considered the corresponding M bus you can say that the main transformer bus connected to the M bus here. So, what happens that if a grid system network system fault happens to be there, it finds a path through the star grounded, it finds a path through this path and then circulating current goes to this one. So, that implies that for line to ground or system side fault, grid side fault, with the arrangements of such transformer arrangements, the zero sequence current flows. So, zero sequence current being not influenced by renewable plant, because it does not go to the renewable plant side. You see here from this part only you can say that this corresponding transformer impedance, the main transformer impedance, it is associated, it is not associated with the grid side impedance. So, therefore, it is not influenced by the renewable plant and the system follows homogeneous nature, as you can say that already you can say we have discussed in our earlier transmission system protection. So, this is only related to zero sequence perspective, zero sequence you can say. However, these you can say that approach of protections like in a conventional synchronous generator, we see that involved with ground faults only. So, therefore, in case of ground fault, zero sequence current based protection schemes will not be affected even in the presence of renewable plants with such transformer connection, and that is what the significance of transformer connection. Now, we will have a test systems before going to different network protection schemes. So, this is you can say that a 39 bus New England systems, we have modification some here. So, to integrate the corresponding renewable resource 345 kV 60 hertz, and at bus number 33 here we replace the corresponding synchronous generator by PV plant with the inverter interface, and with adding to consider the transformer perspective. The inverter with this solar plant is controlled in synchronous reference frame with feed forward compensation. These were the scheme of control being used. The solar plant is set to ride through the fault, providing dynamic reactive power support as per the utility grid code requirement. So, that is what the reactive support is being provided. Now, this you can say that red dotted portion, we have taken the corresponding equivalence for this to have the test of the system. So, this is you can say the solar plant perspective, this part, and then at this you can say that bus number 19 you can say that we have this so called our M bus equivalent, and the bus number 16 you can say that we have this corresponding N. So, these network connections, for this you can say that how the corresponding line protection works, that we like to see. So, for you can say that faults in this particular line. Now, same system equivalent part we have considered here. So, consider that the distance relay is at bus N. So, what are the associated issues and how does it function, functions it correctly or not, that we like to check. Fault is at F, line phase A to ground fault, in this you can see that line with associated RF. So, first we are talking about fault type classification. So, for fault type classification, if you remember you can say that it primarily uses the current based approach. So, let us see the current data at bus number 19 here for a fault in line 1916, pre-fault current you see here pretty balanced, fault data phase A to ground fault. So, you can say that see here the current nature here contributed by the solar plant. So, this you can say that current through which flows there is relay is contributed by the solar plant, phase A to ground fault, but the nature of fault current you see here that is rather you can say that phase A current has gone down, and it tries to balance the corresponding current even though phase A to ground fault happens to be there. This leads to the delta I positive sequence change in current from the fault current to the pre-fault current. So, this delta I 1 you can say that happens to be 0.24, and the I 2 current happens to be 0.03, and I 0 current happens to be 0.53. Note that this I 2 current is pretty small, insignificant here as already mentioned, and the zero sequence current we can it finds a path. So, that is why it is of significant value. Now, what happens that when we translate the corresponding positive sequence, negative sequence and zero sequence current into this classification plane. So, we take the corresponding AG fault, the corresponding I delta I in this reference, and with respect to that the corresponding I 2. So, then the corresponding point which we are getting for this case is at this point, this star point mark here. Fault is AG type, but this happens to be the corresponding angle delta I positive happens to be minus 124.37 from this calculated one, and that you can say that lies in this actual that for this mean for the CG you can say that fault type. So, this area is marked for the fault type of phase C to ground and this angle falls in this one, even though the fault is of AG type. So, therefore, you can say that this classification or current based classification approach fails here looking at this perspective, and the D region you can say that we see here that how the corresponding current modulation happens to be for the phase A to ground fault. And also you can say that the other one you can say that associate the zero sequence current with you can say that the reference and the corresponding I 2 that also falls, you can say the corresponding angle falls outside the zone of you can say that CG. So, it is this also does not say about you can say that the type of fault of AG type of fault also. So, that means that the fault classification example here demonstrates that the fault classification approach may fail in the case of a transmission network connecting to a PV based power plant integrated with inverters. Now, we will try to analyze this. So, this current angle based fault classification logic, if you remember, that started you can say that the associated current which is fault current passing through the faulted path and the corresponding network positive sequence, negative sequence and zero sequence, let us say for a phase A to ground fault, they happen to can say that to be series with 3 RF, and then this faulted path current you can say that the positive sequence and the zero sequence and negative sequence happens to be, you can say that they align certain angle, and this sequence network from the sequence network for the consider the faulted path current that reveals the corresponding the angle, different angles for different types of fault. So, our concern you can say is based on the faulted path current, and in case of synchronous machine based approach we say that the homogeneity angle of the corresponding throughout the M bus side and N bus side will be maintained, and from that angle we consider that the local data also will able to reveal the corresponding phase angle information for the application of fault classification. But now you can say that the angle of the impedance angle of the solar plant being much different, that of the consider grid side you can say this, and that also that of the transmission system. So, the homogeneity consideration is no more valid and that puts challenges. So, let us see consider that what you have learned in lecture 19 of the reference the module 5 you can say that that IF equals to delta m plus delta n contributed from this side and this side. System impedance homogeneity in synchronous generator based conventional approach allows this technique to be using the local you can say that superimposed component. Now, let us see can say that bus 19 data and bus 16 data. So, during fault. So, bus 19 data delta I1, I2 and I0 we have already seen earlier slide. At the same for the same fault the box 16 data delta I1, I2 and I0. You see here the angles are almost same. So, this is what you can say that we are talking about the homogeneity nature, and if you see here this angle, these angles are different, and that to say I2 is of insignificance. But if you see this faulted path current which is a summation of this current and this current, so this I1 current if you see here 0.68, 0.67, 0.67 and the angle same. So, this for phase A to ground fault, and that is why I can say that the IA1, IA0 and I0, I0 and I2 they are all same, we can say that for the 3 phase for the line phase A to ground fault, and that is what you can say valid here. So, therefore, we say that we observe that in such a situation also the faulted path current maintains that current relation, the angle relations for the current for the fault classification business, but the local data at the converter side resource does not hold good because of the converter control different control aspects, but grid side still is valid. So, that you can say that is the big difference you can say that with synchronous machine based approach and the renewable resource based approach. Then this non-homogeneity and all these things what is being introduced relates to that because of this impedance of this equivalent impedance of the solar plant and its associated angle. Now, then to overcome this, what is the solution for the relay? Now, the probable solution is if sequence current angle in the faulted path, sequence current angle in the faulted path, that what we are talking about here, can be obtained by any means, then the fault type, that classification approach which we have used in transmission network protection earlier with for the distance length different applications can be further used. And for that you can say that the below reference provides that information. Next we will go to the directional link application, directional link perspective in the presence of renewables. So, same system and same fault, you can say that we are talking about AG fault here. So, pre-fault data, fault data. So, for directionally link we use both voltage and current. So, pre-fault current sets and voltage sets, balance in nature. Now, fault data already enumerated, phase A to ground fault and the corresponding voltages. Phase A voltage goes down, phase B, phase C voltage remains almost of similar magnitude, though they are also affected as compared to the pre-fault voltages. Now, for this forward fault for bus number 19 IM, this is what we are talking about. Let us see, you can apply the positive sequence quantities, negative sequence quantities and zero sequence quantities, best approach and superimpose and so and so. Using positive sequence quantities, we found the V1 and I1 for the fault using the fault data, and the angle of I1 minus angle of V1 which reveals the forward fault or reverse fault. This angle is coming to be positive, which means that this is a reverse fault. Reverse fault means this side, whereas the fault, actual fault is in the forward fault. So, then this is incorrect. So, that is what, due to the control actions provided by this, so the modulating current is creating problem in terms of that. Negative sequence current, you see here the negative sequence current is insignificant. We have already mentioned that the control action does not allow negative sequence current because of the balance control approach. So, this small amount of current becomes unreliable. So, we cannot rely on the negative sequence current. So, this is also rejected. Using zero sequence quantities, this is a phase A to ground fault, we say zero sequence current will flow. So, significant current is flowing and then the angle of I 0 minus angle of 0 is almost 90 degree, and this is able to correctly identify the fault. And we have already reasoned it out that because of the transformer connections, so the corresponding zero sequence current, significant zero sequence current flows, you can say that, and that you can say that has no relation with the solar plant side. So, therefore, zero sequence current based approach of fault classification will hold good, but mind that this is limited to only ground faults. Using superimposed phase sequence quantities, we know that the corresponding positive sequence currents get modulated, we have already seen. So, if you look back, you can say that to the delta V 1 and delta I 1 superimposed quantities. So, we got this, you can say from this fault data, and then if you say delta V 1, angle of delta V 1 minus angle of delta I 1, that comes out to be 66.29 degree positive. Again, the superimposed component also identifies it incorrectly. This is a forward fault, but this identified as a reverse fault. So, this from this you can say that conclusion we made that negative sequence is not available, positive sequence or the superimposed component they fail, only the zero sequence component approach based approach, fault classification approach, a fault directional link approach provides the solution, but that has a limitation to the corresponding ground fault involvement and subject to the transformer connection as here. So, another problem generally generic solutions for other types of fault, and so some literature suggests about to have, you can say that the controls, you can say schemes embedded here should be modulated, so that the conventional directional link can still hold good. So, that the corresponding angle during that fault situations current between voltage and current still holds good what you find for the normal synchronous generator based approach. Now, we will see the third example on distance link with renewables. So, for the same system, equivalent system of the 39 bus system, see line number 1916. So, we created fault at 80 km from the bus 19 with a fault resistance of 20 ohm and the fault type is BCG fault type. So, what we see here is that the line length is 200 km and line parameters are positive sequence same as negative sequence and 0 sequence provided here. Now, for this you can say that BCG fault, the corresponding Z apparent equation is BB minus BC upon IB minus IC, and then if you put this you can say that data provided here, the corresponding fault data, so that becomes equals to 37.31 minus J 47.92. So, this part is negative, it means that the point corresponding point becomes here. Whereas, the fault is at 80 km in the forward direction. So, that 80 km corresponds to 80 into the positive sequence impedance of this 1.6 23.2, that is the, that should be the correct you can say that apparent impedance the relay should be able to calculate. Whereas, the relay you can say that for this signal getting you can say Z apparent to be this much. So, the Z apparent seen by the relay becomes this you can say that a red point here as compared to the which should be the ideal one actual, and you can say that at this point on this line the line impedance on the are explained. So, for these zone 1 protections the corresponding relay at distance relay will malfunction, it is not able to find the corresponding fault in the zone 1, that is the challenge. Now, we will try to analyze you can say that why that is happening in the distance link perspective. Solar plant connected to that same system. First consider for clarity 3 phase fault. For 3 phase fault V apparent equals to Z apparent equals to VA upon IA or VB upon IP or VC upon IC or V1 upon I1 and so. So, here we are talking about V1 upon IM. So, that equals to distance of fault x into Z1Mn line impedance positive sequence ZMN plus the modulating factor of you can say that I1F upon I1M into RF. So, this is the corresponding voltage at this point Vf you can say that modulates. So, this equals to x Z1Mn plus delta Z, this is what we have learned in the distance relay derivations of equations and so. For this delta Z which corresponds to this you can say that modulating part, you see here for a normal synchronous machine based approach where homogeneity is being maintained. So, you see you can say that if this is the line impedance of up to the x point, so x Z1Mn, then this part because of the homogeneity angle of I1F and angle of I1M, the angle will cancel. So, this is RF, so this will be horizontal line. So, the Z apparent will be this one, and based on that we propose quadrilateral characteristic and so. So, to accommodate you can say that more and more RF for fault involving ground and so. Now, see the situation when the solar plant happens to be there for this case. So, this part you can say that I1F and I1M no more homogeneity, and therefore, that angle will be retained by that, and that angle retaining you can say that makes the corresponding this modulating line to be either downward or upward, and therefore, Z apparent you can say it becomes this or that as compared to this kind of thing. So, no more horizontal line, it will be modulating you can say that in the downward and upward, and furthermore, you can say that the magnitude of this you can say that of this part becomes a factor of concern depending upon the that depends upon the control aspect of the solar plant also. So, this you can refer to in lecture 26 you can say that for in module 5 you can say on this perspective. Now, come to BCG fault. So, BCG fault as you have seen in earlier example last slide, Z apparent equals to BB minus BC upon IB minus IC at bus M, and that become equals to x Z1Mn plus a modulating factor of this current IB minus IC IBF minus ICF upon you can say that IBM minus ICF into RF, and that equals to x Z1Mn plus the delta Z part. So, fault call and limitations from renewable plant increases the delta Z significantly. You remember, current is limited, it means that impedance is more. Non-homogeneity, you can say that is another issue. For the large scale, you can say that phase angle deviation from the normal situation of with synchronous generator also. In the last example, and for this delta z, the modulating factor, there are two parts, RF and this current, you can say that angle current ratio part. So, the current ratio magnitude is here for this case with for the last example data becomes 4 and its angle becomes minus 63.34. So, this angle shows clearly that non-homogeneity is not maintained, and that is you can say that about that angle issue, and this magnitude of these 4 imply that you can say that it is a large variation, you can say that on the delta z part, and that is why you are dictating on this perspective. So, therefore, we say that the Rayleigh malfunctions, you can say that is due to this non-homogeneity, the angle introduction, and then you can say that the angle ratio, you can say that magnitude also may be of significant because of the current limitation by the inverter based renewable resource. Then what is the probable solutions? If fall path current angle can be obtained like we saw in the classification perspective, fall classification perspective, the relation can be improved by compensating the deviation associated with delta z. So, some you can say perspective there. This reference reveals such an approach to mitigate the issue of you can say the distance relay performance in the presence of renewable resources. In overall, we see that renewable resource plants are being integrated in general with inverter interface, and they modulate the voltage and current signal differently during fall as compared to the synchronous machine based approach. Homogeneity, that the angle issue of the angle of that plant, equivalent impedance of the plant is much different than that of the synchronous machine or the transmission system. This is a current source, not unlike the voltage source, you can say that, which you take for the synchronous machine based approach, no net sequence current. Further, for the important point is that integration of large number of such converter based approach, the inertia, there is no rotating part here, the inertia becomes less. If the penetration of such renewable resource becomes more and more, system inertia reduces accordingly. So, therefore, what will happen that during a swing operation also the swing frequency will change, and therefore, in that situation the traditional power swing blocking settings and the principle associated which we have learned in the distance relay are under scrutiny. Perhaps differential protection may be a better choice in this perspective, but we have already learned that line differential has limitation in terms of synchronization issue, line length, communication, associated communication cost and failure chance also, and furthermore line differential you can say that cannot provide backup protections. So, with this we can conclude on this network protections with renewable resources. Thank you.